introducing it in this very kind of abstract theoretical context in which a Riemann sum does not necessarily represent area anymore. It's actually just a sum of the products of bunches of things. Okay, and I'll have more to say about this as we continue. All right, and now is an exciting moment in your lives. We're now going to talk about integration. Oh yeah, that's right. I kind of mentioned it at the very end of last time, but now I'm going to really talk about it. All right, what is integration?
Oh no, we're not
All right,
doing this again.
basically, yeah. Oh, that's coming up. That's coming up in like 5 minutes.
What is the matrix of like 6 and what is the matrix?
All right, what is integration? Loosely speaking, integration is these things that we've been doing. Integration is the process of finding the area under a curve. Okay? And so, but I'm now going to give a formal definition of what an integral is. Okay, so ready? Here we go. The integral, whoa. Yeah. The integral of f from x equals a to x equals b, which I have a notation for, and the notation looks like this. It is this kind of weird curly S thing, and we put the a here, and we put the b here, and in here we put the function, and yeah. Okay, that is called an integral. And an integral is the limit of a Riemann sum. So this is the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I star delta x sub I. In other words, the integral of a function on an interval is what happens when you take that interval, partition it in some kind of way with potentially unequal subintervals in some kind of good way, pick a sample point from each subinterval, add them all up, and then take the limit as n goes to infinity. That is called an integral. All right, and I want to introduce you to certain exciting features of this integral. First of all, there's a name. First of all, this function, the function part is called the integrand. And if someone could erase, and these guys are called the limits of integration. The limits of integration. The guy on the bottom is called the lower limit of integration, and the guy on the top is called the upper limit of integration. They're just the left and right. They're the left and right endpoints of.
I'm still thinking of comp size, so I accidentally wrote it.
Okay, they're the left endpoint and the right endpoint. All right, so there's now a beautiful story to tell. Shari, you just got all this lecture yesterday, right?
Yeah.
Yeah, we're just running it all back. That's what it is. All right, so there's a story now, and it's a story of infinity, and it's actually related. I think we talked about this before, depending on maybe I don't know if it did in all classes, but remember how we talked about the Leibniz notation for derivative? We wrote like dy dx, right? And we discussed why is that notation so great? This means derivative, but what's so beautiful and wonderful about this notation? Okay, besides differentials, even before we talked about differentials per se, what made this notation sort of like intuitive and helpful?
That's what the slope is, like.
Because that's what the slope is. Yeah, yeah. Okay, what is this supposed to remind you of?
Change of y over change.
Delta y.
Yeah, but you can't talk. Delta y. Yes, this is the limit as delta x goes to 0 of delta y over delta x. In other words, what made the Leibniz notation so great is that it is kind of like a infinity version of something that you did in Algebra 1, which is change in y over change in x. Okay, so it's like this. This is like a real number. This is the change in y. This is a real number. It's the change in x. And now what we do when we take the limit as delta x approaches to 0 is we're making everything infinitely small. So it's kind of like you sprinkle the magic calculus pixie dust onto delta y over delta x, and these finite things get converted into these infinitesimally small things. Okay, we think of dy as being an infinitesimally small quantity, and dx as being an infinitesimally small quantity. Okay, the same thing is going on here. We are taking the magic calculus pixie dust, and it's just like it's like the Cinderella story. Okay, so in Cinderella, there's like a girl. I still don't know this. What's the story again? I can't remember what. She's like very poor, but she's not really
poor.
Her parents, her mom is mean. Her stepmom. Okay, right. So in the Disney version, the stepmom is really mean. The stepsisters are like really mean and kind of like ugly also. And Cinderella has to like clean out the like fireplace or whatever. The cinders. Yeah. Okay. Good. Right. And then she wishes for
Not the fairy godmother.
Yeah, the fairy godmother comes. Yeah, who doesn't have a prom date still in this class? If you pray, your fairy godmother could come and should send you to the prom. She wished on a star. Yeah, right. Okay, good. So for today, I will be the fairy godmother, and I am going to sprinkle some. We're talking about Cinderella because there's the bippity boppity boop scene where she sprinkles and all the things turn into other things.
Yeah.
So yeah, we did this yesterday. So let's see. You sprinkle the dust on the mice become horses. The pumpkin becomes it's really necessary. The pumpkin becomes the coach, and then the carriage, whatever. And then there's like one or two more things that become other things.
Her dress.
Her dress gets fixed.
Dress gets fixed.
There's like mice somewhere.
There might be like one
I
other
thought
thing.
the mice turned into horses.
There's a chairman.
Yeah, there's like a chair. There's a
Footman. Is the cat the footman? No.
I'm pretty sure the mice are the
It's another
No, the mice are the horse.
Okay, he's looking it up. But meanwhile, okay, so wait. Alright, back to calculus.
I thought that was Cinderella.
So what is the point of all this? The point of all this is a Riemann sum before you take the limit is a finite object. Stephen, these are all finite things, right? This is the width of an interval. That's a number. This is the value of a function at a sample point. That's also a number. And we're adding them all up, okay? But now, as we sprinkle the magic calculus pixie dust on this Riemann sum, watch what happens. This Greek letter, sigma, making an S sound because sum, becomes, after we sprinkle the magic calculus pixie dust, into a sort of infinite sum, which turns into this curly S. Note that is like the infinite kind of version of this, okay? There's more. Now, watch it, wait. The widths of all these intervals, as I said, if it is a good partition, as you take the limit as n goes to infinity, the widths of all of these things go to 0, right? So notice as the delta x, which is a finite thing, when you sprinkle the magic calculus pixie dust, turns into dx, which kind of represents like an infinitesimally small like width, right? So that's what the dx is. It's like this infinitely small width of the subinterval. And here we are sampling the function once per subinterval. As n goes to infinity, the number of subintervals goes to infinity. So I used to be sampling, if n is 100, I'm making 100 sample points. If n is like a million, I'm making 1,000,000 sample points. As n goes to infinity, it's like I'm sampling the function infinitely often. And if I'm sampling the function infinitely often, it just turns into the continuous function f. Okay, every piece of this formula on the left has its sort of finite analog on the right. Is everyone clear about this? All right.
It doesn't turn back at midnight though.
Doesn't turn back at midnight. Yeah, that would be terrible. All right, so, good. You now know what an integral is. Let's do some integrals. Yeah, of course. What is the integral from 0 to 5 of x dx? Well, you can't talk. Well, an integral is kind of just the limit of a Riemann sum, right? And the limit of the Riemann sum will tell me the area under the curve. So, for now, what's the way I should do this? Just draw a picture and do it, right?
Just do it.
So, draw a picture. Do you know what the x function looks like? And we are integrating from 0 to 5, which means that 0, 5 is my like interval. And an integral is just the limit of a Riemann sum. So the Riemann sum, if I do it correctly, is supposed to measure the area of that triangle. So what's the answer to this integral? 25 halves. You just did your first integral. Integral by duh. Okay, here's a bunch more. Integral by geometry is actually fun. So integral from 2 to 5. What's the integral from 2 to 5 of just like the 7 function? Touch. And I'm just going to put a whole bunch more up there. Up here.
I was like,
Wait.
Symbols are similar, but they're totally different things. Oh, maybe we should talk about this now actually for a minute. Yeah, I forgot about this. Let's have a philosophical conversation about what an integral really is. Okay, so actually this is a good opportunity for us to just completely review our philosophical assumptions. It's a good thing to do every now and then. Okay, so let's go through every object that we've introduced so far in this class and talk about what they really are. What is, almost, not quite that far back. What is, okay, we can start with that. What is a limit? A limit is a, assuming it exists. You don't have to talk. A limit, assuming it exists, is a number, right? A limit is a number. Okay, good. What is a derivative of a function at a point? Slope of the tangent line, all true. Instantaneous rate of change, all true. But I don't want those kind of answers, even though they're all correct. I don't want to know what it means or what it represents geometrically or what it's used for. I want to know like what it is, like what kind of a thing. Yes, the derivative of a function at a point is a number. No, it's a number. The derivative at a point.
Oh, at a point.
Derivative at a point is going to be the slope of the line, which is going to be a number. Right? Derivative is a limit, which, assuming it exists, is a number. Okay, so that's the first thing we did. The second thing we did, really on the same day, what is the derivative of a function? It's another function, right? It's a function which outputs derivatives. Share, stop doing that. The third thing that we did like last month, what is an antiderivative? Almost. What is the antiderivative of a function? Yes, the antiderivative of a function is technically a family of functions, all of which are vertical translations of each other. Okay? So now the last really major thing that the last new concept that we're learning this year is an integral. What is an integral? What kind of mathematical object is it? It is a number. An integral is a number. I probably should write somewhere like that this is the integral, assuming this limit exists, but they always will. Assuming this limit exists. Okay, so good. Good. An integral is a number. It's a limit of a Riemann sum, but assuming that limit exists, then the integral is a number. Okay, good. So do all these integrals. Do that one, do this one, do this one. For all of them, you do the same thing. You just draw a picture, and it just works.
wait, which one is 4? Which one is 3? Which one is 4?
I don't know. Doesn't matter.
Section on the bottom.
That's like how you did this class. You just do it.
Was it the area under?
Oh, it's another triangle. Wait, is it arrow 2?
Makes a difference, yeah.
36 times 9 over 2.
Wait, what?
Too lazy.
It's just
Split into a
Here, this is like a trapezoid, right? That's one way to do it, yeah. Or you could just go straight to the trapezoid. That's 3, that's 3, that's 9. So this is like, yeah, the picture's kind of weird shape. But it's like the average of the bases times the height. So is that just 18? Or did I just move wrong? 18, right?
I didn't do anything. That's not on your pencil.
This is the 2 by 2, so it's like
My phone.
2 plus 9
2 plus 9 halves,
halves.
yeah.
I thought he was sitting on it.
So 15 halves.
You guys getting these all right?
Yeah.
Cool. How about the one on the top right? It's like a thing. You recognize that function? It's like a pre-calculated thing.
Oh, that's a circle with the radius of
Semicircle.
semicircle.
No, it's a semicircle.
Semicircle.
Wait, is it a quarter or is it
Semicircle.
It's technically a quarter.
Yeah, that's it.
I was like, wait, does it go all the way down?
Wait, why doesn't it should go all the way? Oh, 0. Okay.
Right?
I would argue that it's actually still semicircle.
Okay, do we even?
We're only looking at one part of it.
Okay, wait. We only have a few minutes left. This is like the most important thing. What is the integral from -4 to 2 of x? Draw a picture and think about it.
Oh.
Things are getting a little weird. We have to talk about this.
Like anti-area.
Yeah, kind of. This is potentially a little tricky, so I want to make sure everyone has got this conceptually under control.
So how does this work?
Yeah, so how does this work? Okay, so let's talk about it. Here's the point at which, like 10 minutes ago I said integration is kind of like finding the area under the curve, okay? But it's not exactly finding the area under the curve. It is like that, but it's different. Because integration is more general. Technically speaking, an integral is just the limit of a Riemann sum. And if you look at the way I defined Riemann sum, I did not particularly say anything about area, right? In fact, the one thing that all the functions that we've looked at so far have in common is that they're all positive, right? So how do we deal with functions which are sometimes negative? Well, let's just think about it. What does this Riemann sum thing do? This Riemann sum says, get in there in that subinterval, plug a point in, and see what the value of the function is. If I should happen to plug a point into a function, and I get a negative y value, what happens? I have a negative y value. I multiply by my delta x, and thus I have a negative, thus my ith, you could call it a rectangle, but it's not really a rectangle anymore. It's just a product of a width and a function value. That one will be negative. So I'm adding up a whole bunch of things now, and some of the things I'm adding up are negative, and some of the things I'm adding up are positive, and that's just that. So can an integral be negative?
Yes.
Definitely. And if you want to think about it in terms of rectangles, you kind of can. But remember, if I pick an arbitrary point, somewhere in that first subinterval, and I plug that into the function, and I should happen to get a negative y value, then when I multiply the width of that interval by that negative y value, I have a negative quantity. So I call these, informally, I call these upside down rectangles. Upside down rectangles contribute negatively to, not a technical term, but it's a thinking term, contribute negatively to the Riemann sum. Are you guys with me?
Yes.
And I just keep doing this. Here, when I pick an arbitrary point, I also get a negative rectangle, which contributes negatively to the Riemann sum. And like, again, and like, again. And now over here, I get positive stuff. So, that being said, what is this integral? -6. Good. That went really well. Yes, it's the sums of a bunch of things, all of which are products of functions and widths. Okay, so some people like to talk about positive area and negative area. I think we should kind of avoid that, but some teachers talk about that. An integral is really like the net signed area. It's the amount, it's the positive of minus negative. Is everyone okay with this? All right, if you are good, I am good. I have two things to pass out to you.
I thought I was doing a good thing.
The first thing is a worksheet. Can you, Sandeep is giving everybody a worksheet. The second thing, can I have your attention for like one more minute? The second thing is this AP practice questions. Can you give everybody one of these? You may have heard that there's a calculus AP exam. It was on Tuesday, so you missed it. But it will be taking place next year again, and by then you will have actually learned calculus. So you should take that then. In order that, and we're going to teach you, me this semester and Mr. Stein next semester. Between the two of us, you will learn everything you need to know to be very, very ready for the AP exam. But it is good practice to do some practice AP exam questions. So from time to time, I am going to give you some AP questions, and you need to do them. So if you look at this. These are free response questions. You get when you actually take the AP exam, you'll get 15 minutes per question. These are to be done without a calculator. And I'm going to collect this and grade this for accuracy. So this is a formative grade. It'll be due on Monday, I guess? Yeah.
60% be like a 100%?
No. No. So the rules for this are, you can use your textbook, you can use your notes, you cannot use any people. So you cannot get help from other people in this class, other teachers, your parents, or the internet. But what's up? Videos are okay, yes. And just be very careful that you follow the directions. When it says justify, they mean like justify, like magic sentences, etc. So this will be due on Monday. Any questions about this? These are about the easiest AP questions that I can find. So they probably won't even take 15 minutes each. They'll take you 10 minutes each or whatever. All right, there's a worksheet. There's also stuff in the book. I'll see you guys on Monday. Thank you for coming.